We're looking at 10.4 to 12.3, review worksheet 1. So one problem is, the first problem is an application of the position function for a projectile. So neglecting air resistance, the path of a projectile launched from initial height h with initial velocity speed of v sub 0. Angle of elevation theta is described by a vector function. So the v sub 0 cosine of theta ti represents the horizontal component of the position, and then the vertical component is provided by this equation here. Okay. All right. So G is the gravitational constant. Okay. So number one, the baseball hit from a height of 2.5 feet above ground with initial velocity of 140 feet per second and an angle 22 degrees above the horizontal. Determine whether the ball will clear a 10-foot high fence located 375 feet from home plate. All right, so we can begin to plug information into our RFT equation, our position equation. So 140 is going to be the v sub 0. It's going to be initial velocity. 22 is the angle at which the ball is being hit above the horizontal. And then we can also plug in 2.5 feet as the initial height off the ground. And then the velocity, 1/2 g squared. We have 32 feet per second, and then divided by 2 would be 16, so 16t squared, j component. So we know that the horizontal distance we'll travel is 375 feet. So we can set 375 equal to the horizontal component, 140 cosine of 22t. And then we can just simply solve for t. T is 2.889 seconds. So we know that information about time. So part B says determine, okay, part A still. We want to see is the ball going to clear a 10-foot high fence. So that means at 2.89 seconds, when it has traveled 375 feet, is the height at this moment in time going to be at or greater than 375? Okay, if it's lower than 375, then we know that if the height is lower than 375 at this time, at 2.89 seconds, we know the ball is not going to clear the fence. So we're going to plug 2.89 into the vertical component of the equation. So 2.5 plus 140 sine 22 times 2.889 minus 16, 2.889 squared. And if we add those terms together, we get 20.47 feet. Okay, so is this going to clear the, sorry, not 375 feet. 375 is the horizontal component. The vertical component is it going to clear the fence? The fence is 10 feet high, so it needs to be above 10 feet. The ball is at 20 feet above ground at the moment that it crosses the 375 feet distance. So therefore, we know the ball will clear the fence. All right, determine the maximum height. The maximum height will occur when the y prime is equal to 0, when the vertical component is the rate of change of the vertical component is at 0. So we can find y prime and set that equal to 0. So here's y prime, here's y of t. So we can find the derivative for each component. 2.5 is a constant, goes 0. 140 sine 22t is a linear, so the derivative will just be 140 sine 22. Negative 16t squared, the power rule derivative will be negative 32t. So we set that equal to 0, and then we solve for t. So the ball will reach its maximum height at 1.639 seconds. So it says find the maximum height. So we can plug 1.639 back into the vertical component of the position function. And when we plug 1.639 in for all the t values, we'll get 45.476 feet. That's the maximum height. Okay, determine the distance horizontal from home plate when the ball hits the ground. Okay, we know the ball will hit the ground when y of t is equal to 0, when the vertical component is at 0. So we can set the vertical distance equal to 0, y of t equal to 0. So we can use our calculator to set this equal to 0 and simply look for the x-intercept, and x-intercept will occur at 3.325 seconds. So then the horizontal distance would be 3.325 plugged into the horizontal component, the 140 cosine 22 times 3.325, and the distance will be 431.604 feet from home plate. Okay, let's look at the back. Number 2, an object moving along a curve has position x of t, y of t, and we're given dx dt, and the derivative formula for dy dt is not given to us. At time t equals 2, the object is at position 1,8. So find the x-coordinate of the position of the object at time t equals 4. All right, so let's think about this way. If we want to find the final position of this object, we think of it in terms of component form. So we know the final horizontal position will be the initial horizontal position plus the horizontal displacement. So I'm trying to find the position at time t equals 4. Okay, so what our starting point is, what we do know is we know x of 2. So the initial plus however horizontal distance we travel, the displacement between time t equals from time t 2 to 4. So x of 2 we know is 1. And then the integral of from 2 to 4 of x prime, we just use our calculator to find that value. So 6.132 plus 1 is equal to 7.132. Part B, we don't know what the derivative function for dy dt is, but we do know the value of dy dt at time t equals 2 is -7. So it says write an equation for a line tangent to the curve at point x of 2, y of 2. So if we want to find the tangent line equation, we need a slope. So slope is dy over dx, right? dy over dx is slope. So if we want to expand dy over dx in component form, it's dy dt over dx dt. So we know that dy dt at time t equals 2 is -7. We know dx dt at time t equals 2 just means that we have to plug 2 in for the dx dt equation, and then we're going to be able to find the slope. dy over dx is the slope. We get -2.983, so we have our slope, we have our point. Now we can write our tangent line equation. So y minus y sub 1 is equal to m times x minus x sub 1. Part C, find the speed of the object at time t equals 2. So the speed is going to be the magnitude of velocity at time t equals 2. So speed is x prime t squared plus y prime t squared. Replace 2 in for t values. So we know x prime is 3 plus cosine of t squared. So replace 2 in for t. And then y prime of 2 we know is 7, so 7 squared. And then we just use our calculator to simplify that to get 7.383. Okay, part D. For t squared is equal to 3, the line tangent to the curve has a slope of 2t plus 1, which we know is dy over dx. Find the acceleration vector of the object at time t equals 4. So acceleration vector, that means we need to find the horizontal and vertical component at time t equals 4. So the easier portion is to find the horizontal component of the acceleration, because we know dx dt, so we can just evaluate the derivative of dx dt at 4. So use our calculator for that. If we do n deriv the horizontal component at 4, and we get 2.303. So 2.303 will be the horizontal component of the acceleration vector. Now to deal with the vertical component of the acceleration vector. But what we're going to do is we're going to see if we can arrive at the equation for dy dt. Because if we arrive at the equation for dy dt, then we can do n deriv of dy dt and then plug 4 into that derivative function. All right, so we have an equation that will allow us to get dy dt. We know slope dy dx is dy dt over dx dt. We know what dy dx is, since that's given to us. The slope is 2t plus 1, so slope is dy over dx. And we also know dx dt, which is 3 plus cosine t squared. So if I solve for dy dt, if I do cross product, I can then have an expression for dy dt, which is 2t plus 1 times 3 plus cosine t squared. This is my vertical velocity function. So if I find the derivative of this, then that will get me to the vertical component, the acceleration vector, and then I can plug in 4. So I can just call n deriv of my dy dt, and then plug 4 into that derivative function, and then that will give me 24.814. So that's the vertical component. My horizontal component, vertical component, this will combine to give me the acceleration vector at t equals 4.